Hi everybody. In this video we're going to go walk through the lab for module 5. So we're going to walk through all of these labs, and this is going to be kind of a tutorial. We'll be walking through stat powers as some of the documentation is lacking right now, and so we'll just follow along, and so you'll see in this kind of a walkthrough of what we need to do. Now, this lab is on qualitative inference on the fundamentals, which is essentially we're looking at proportions for a single sample, like a single population, and we'll kind of just jump right in. So this first is actually related to sampling distributions. So part of this is this module, we're going to be concerned with understanding how the central limit theorem works. So here we're going to look at the idea of sampling distributions. So in this lab, we're going to see in which the ways in which statistics from a random sample of data can serve as point estimates for population parameters. And so this is kind of the idea of a sampling distribution, like every time you sample, what like a distribution will the sample statistic kind of be drawn from. That's the idea. Just as a random variable has a distribution, sample statistics can be modeled with a distribution as well. So the data, we're looking at a 2019 Gallup report, some data from the let's see, the premise that scientific progress benefits people has been embodied in discoveries throughout the ages, from the development of vaccinations to the explosion of technology in the past few decades, resulting in billions of supercomputers now resting in the hands and pockets of people worldwide. Still, not everyone around the world feels that science benefits them personally. So, okay, we're going to be opening up a simulated population, and we'll be asking people the question, do you believe that that the work scientists do benefit people like you? So I'm going to pull up this population. I'm going to put it over in the other window, in fact. And really there's only one variable in this. It is scientist work. Well, we're going to create a sample from this population. We're going to get a sample of size 100. And so that's the only thing we need to do to sample from it. We don't have to actually build the population. And I'm going to sample, and we're going to see the question. They're asking, does scientist work benefit people like you? And they say benefits, doesn't benefit. So this is the kind of output we get. All right. So there's our output. We're going to do some analysis here, and we're just going to click Analyze as a variable. We're not interested in doing time series analysis. Very simple kind of data set because it's a categorical variable. And so let's see. We want to look at the bar plot. So let's look at a bar chart. Okay, so this is a good way of kind of visualizing the proportions or the frequencies. Frequency is how many people said, yes or no to this question. It looks like we got 80 people who said yes, and I'm going to say probably that we got exactly 20 people who said no, since there was. Now we can actually look in the summary statistics, and it gives the frequencies there, 80 and 20, indeed. This is just to give you a sense of how we can kind of sample from this population, but let's think about how good of an estimate we'd get to this population parameter, because really I don't know what the population parameter is. You can actually unlock it if you click here and input the key phrase, which in this population happens to be 5374572. Hit enter, and it unlocks the whole thing, and we can see that this was built with 80% to be the proportion. So I was lucky for this example. You do the same thing and you're probably not going to get 80% in your sample. But anyway, let's continue through the lab. So we're going to generate a new sample of size 50 and open analysis. So let's open the sample size 50. Here's our sample. I'm going to analyze it as a variable, and now we're going to do a different kind of analysis. Okay. let's just look at I'll look at the summary statistics. We have 86% said it benefits and 14% said it didn't benefit. This is similar to the population, but it's not exactly the same as the population. This is a sample, and it's a random sample, so you're not going to likely get the exact same value as the population. If we wanted to, now here we know the population proportion is exactly 80% because we were able to peek into that. But let's say we didn't and we wanted to try to estimate that. From this sample of size 50, we want to, the thing to think about is this. Like, let's say I'll just close that. I'll sample again, boop, and I'll just analyze it again, and then I'll look again at the proportions. In this sample, 72% said it benefits. And I'm going to just do this a couple of times, analyze as a variable, look at the statistics, 72%. So you can see that I'm hovering around that 80%, but we're not getting exactly 80%, except for that one first time, 0.7 this time. It's been a little bit low. Maybe I'll get above 80% one time. 84%. So yeah, okay. So this is what we mean by a sampling distribution, that every time we create a random sample, we get a different number. Imagine we were to do this many, many, many times, and we want to look at, let's say you were going to do 1,000 or 10,000 samples, each of size 50. What would the distribution of sample proportions look like, theoretically or like empirically? All right, so we're going to simulate that using a binomial probability. So we're going to go now to a discrete probability distribution, the binomial, which is useful for modeling this type of thing. So we're going to simulate just asking a single person with a probability 0.80 of saying yes. So this is what the distribution looks like. A 0 represents the person does not believe science benefits, and 1 represents they do believe it. So we're going to do a big sample, sample of size 50, and I'm going to sample, let's do, as the lab says, I'm going to do 15,000 samples. So we're going to simulate this many, many times. I'm going to click sample. It's going to give me a lot of, so every row here represents another sample of ones and zeros, and over in the last column gives me the corresponding average, but in fact an average of ones and zeros ends up being a proportion, right? Because if you add up all the ones and zeros and divide by 50, what you get is what's the proportion of ones. So I'm going to click Analyze to take these 15,000 sample proportions, bring them into a new window, and we'll do a little bit of kind of poking around at these values and see what we can say about them. I'll fix that. So let's look at the histogram. Look at that. Okay, so there's the distribution of proportions that we saw in our, so this is what you could say is like an empirical sampling distribution. Every time you go out and pull out a sample of size 50, you're going to get a sample proportion. One of these values with the relative likelihood kind of approximately given by the height of the bar. And so let's see, I'll change the number of bins as it's suggested. Oops, I recommend using 20 bins. 20 bins does make it look pretty good. Okay, great. Now this is what's called the empirical sampling distribution. Basically, it's based on a simulation. What you can also do is think about, look at the theoretical sampling distribution using under the sampling menu. There's the sampling distribution for proportions. Here we can kind of put in the parameters of this population by putting in the success of the sample proportion to be 80 and a sample size of 50. Now what this is here showing us is this is the theoretical probabilities for each of these values of the probability that we would get 100%, or or you could think of it like 50 out of 50, 49, 48, 47, 46, 45. So there's a bar for each of these. X representing how many people out of the sample say I believe science helps, and p hat is just the sample proportion. So this is very similar to the chart that we saw before. Of course, this goes all the way down to 0 because there is a theoretically positive probability for those values, but out of our sample, we didn't get any that low, so we didn't have bars for those really small values. If you wanted to kind of calculate that probability, we can say, well, what's the probability that that p hat is like below, let's say below 0.5, which is right here in the middle, and that is 0.0000000057. So in other words, like 25. There's the chance that I would do this kind of a sampling and I would get something like 25 or fewer people who say they believe science doesn't help, or they 25 or fewer that say science does benefit. The chances are so minuscule that out of 15,000, likely I get none, right? I realize, of course, at this point, I actually was simulating the wrong proportion. I was doing the proportion for people who do believe science helps, and in the instructions it talks about using 0.2 for the probability that science does not. It's the same kind of shape, but it's actually the symmetric distribution. But the principle of what I was doing is the same. That the steps are pretty much the same. I think we'll move on to Lab 5.2 on confidence intervals. All right. So if you have access to the population data, then you can say exactly what a proportion is. So the idea here is if you only are accessing a single sample, and you want to make an estimate, a point estimate or a sample proportion might not be good enough. So we're going to use the idea of an interval estimate. So let's walk it through. Roughly 6 in 10 U.S. adults, 62%, say climate change is currently affecting their local community either a great deal or some. This is from 2019, so it's a few years old. So in this lab, we're going to assume 62% is the true population proportion and learn about how the sample proportion can vary from sample to sample by taking smaller samples from a population. Okay, so we're going to use a population's already been built. I'm going to just pull that up. This is a simulated population. And it's similar to the last one. It's just a single categorical question. Does climate change affects? And they're going to say yes or no. I think we're going to go through and we're going to create a sample of size 60. Click sample, and you can see we have a bunch of yeses and a bunch of nos. We're going to analyze the output as a variable, and we can look at answering the questions of what % of the adults in our sample think climate change affects their local community. We can go down here. So we have 61. I got 61.667. You're going to have something different likely. So that would be my answer. I would say my proportion is like 61.7%, say. Of course, this is going to vary from sample to sample. All right. So we're going to go through and create a bootstrap proportion confidence interval. The idea here is to we're going to kind of imagine this is our population. We're going to sample and sample and sample and resample from it many, many times to create a kind of a distribution and figure out what would be the middle 95% of sample proportions roughly. So I'm going to go down to sampling. I'm going to resample from this. I'm going to sample a sample of size 60, and I'm going to do this many, many times. So we're going to create a sample of size 60. Actually, you know what we'll do is I'll take this data, and I'm going to, I'll click Share Data, and I'll just open this in a new tab. That'll be a fast way of bringing the data over. This will help because then I can open up sub windows within here. Okay, so under sampling, I'm going to set the sample size to 60 and say that I'm going to do 10,000. 10,000 is a nice big number, 10,000. With replacement, because I want to potentially get different values from here, I'm going to look at the proportion of yeses, and I'm going to click sample. So it's going to create, it'll take a little bit of time, but it makes all these values. So I have all these proportions, and I'm going to analyze those proportions as a quantitative variable. And I know the reason it's taking a long time is because of the median test, and I can fix that. All right. So we're going to look at the sample summary statistics. Actually, let's look at the histogram. Okay, so these are the sample proportions. These were generated through bootstrapping, which is basically resampling from our sample. So to create a confidence interval, what I'm going to do is look at the summary statistics and estimate what bounds cut off the middle 95%, which is the 2.5th percentile, which is 0.5. Okay, and then for me, if I put 975 as my upper bound, I get 0.7333. So what can I say? I'm 95% confident that the population proportion is between 0.5 and 0.7333 based on my sampling. You're going to get something slightly different. So this is a bootstrapping method as opposed to using like the other methods which can be found under proportion interval estimation. You can just say that I want to look at the proportion of yeses, and so you can see all of these other methods. The approximate normal, uses a normal distribution to approximate. There's the exact method, which uses an F distribution, and some of these others which are mentioned in the notes. They're all going to be pretty similar to each other, and you can see these match nicely with the bootstrapped method, but they're all slightly different because they use different methodologies and different assumptions, and you're going to get slightly different values. Okay, now we're going to talk a little bit about the empirical rule, just to kind of understand a little bit more about the normal distribution. Let's see. No, I think there's nothing much to say there. Inference for categorical data. Okay, we're going to okay, so here we're going to look at some a data set. So I'm going to open up we're going to open up the YRBSS data set. So from data, I'm going to go to type in YRBSS, click load, pull up that data set. So this is the Youth Risk Behavior Surveillance System survey, and so there's a lot of variables here. What I'm going to minimize this data file details window. We're going to be interested in the amount of days students have been texting while driving the past 30 days, and what's the proportion of people who have texted while driving every day in the past 30 days and never wear helmets. So a couple different things we're trying to estimate here. So, okay, we're going to first look at the texting while driving in the last 30 days. Text while drive 30 days. This is our variable. There are some missing values represented by NAs. Ignore NA is there by default, so that's going to be just ignoring any missing values. So we're going to be having a bunch of it looks like we have categories. They're treated as variable, or so these are bins, so it's not treated as a number, because although there are zeros, there's also other values like 10 to 19. Let's look at the data ordering. Let's make sure this is in increasing order. So you can see it goes 0, 1 to 2, 10 to 19, 20 to 29, 3 to 5. Let's move that up. 6 to 9 goes here. 0, 1 to 2, 3 to 5, 6 to 9, 10 to 19, 20 to 29, and 30, and did not drive. This is great. So that's a good ordering for the data. Sometimes StatPowers does not order them correctly because it just does it alphabetically. And yeah, 1, 0 comes before 3, so that's, yeah, because it's using just a character alphabetization. So we can look at the summary statistics. We can see the frequency for each of these categories, and we can see the sample proportion for each of them. So the question that was asked, what are the counts within each category for the amount of days? Well, the counts are given right here, so we get them, and actually a bar chart visualizes it. You can see it goes down, but then like at 30, the number of days somebody texted while driving, there's actually a category that do it every single day. That's actually higher than the 20 to 29. But then there's a lot that don't drive. Interesting. Now the second question was asking about what is the proportion of people who have texted while driving every day in the past 30 days and never wear helmets. So we're going to close this up, and we're going to look at two variables. This is basically what proportion are just reckless people. So looking at the helmet 12M variable, and we're going to open up a contingency table of these two variables. So basically it's a way of showing both in column and row all of the variable values. So you can see what we got. The row variable is the helmets, and then the column variable is what we were just looking at. Now we were asking about people who never wear helmets and text like 30 days out of 30 days. So if you look at the marginal table, what we're looking for is found right here, and maybe looking at but this is a frequency out of 12,384. If I'm looking for a proportion, click it to proportion, and you can see this is my proportion. Out of this sample, 3.7% of the people never wear helmets and basically text while driving all the time. 3.7% of youth. So watch out. All right. I kept my, for the next portion, we're going to go back to texting while driving. I'm going to open that back up because we're going to go back to this. If you closed it, you could just generate this analysis. Again, it doesn't take much time. All right, we're going to look at confidence intervals for this. So let's go down to proportion interval estimation. So we're interested in the question of what proportion of people in the population, not just or youth in the population, text while driving 30 out of 30 days each day. So that's 30. So I'm going to consider a success a 30, and this is 827 out of the 12,665, and so this would be our point estimate. So 0.065. Now another question: what's the confidence interval? Well, there's a bunch of different confidence interval methods. We go through these in the text, but often what's taught is this approximate normal. I personally think there's a lot of drawbacks to that. Generally the Wilson score tends to be kind of tends to be a little closer to the mark, if you have a choice, Wilson's score is usually the best to use. So we're going to use that. Now, it doesn't use a, so this one is a symmetric confidence interval. So you can calculate the margin of error here by just taking the difference between the upper and lower bounds and just dividing it by 2. That's the margin of error. Now, let's look at another question, which is, for those who don't wear helmets, what's the proportion of people who text while drive? So I'm going to open up that other window, and actually we can do this using we can do it here. Well, actually, that would let's go back to our population, and I'm going to do a little filtering. I'm only going to text while driving as the variable I'm interested in, but I'm going to filter it by the variable helmet 12M, and I'm going to select only the people who never wear helmets. Okay, so if I perform this, I'm going to get a different proportion likely. I'm going to consider a success 30. So of people who don't wear helmets, what do we have here? We have 7%, about twice as much, twice roughly. And then you can see the confidence intervals. So let's put these side by side with each other. And we can see that, my mistake. I was thinking it was 0.035. No, it's 0.065. So it's higher, but it's you could ask the question: is there overlap? And for these confidence intervals, these are 95% confidence intervals, and it looks like there is some overlap. So you could that if you were asking, is there evidence that the proportion is actually truly different? Well, if the confidence intervals overlap, that leads you to think that maybe it's possible the proportion is the same in the population, and just we happen to have a higher sample proportion. But yeah, I think this is all I'm going to do for this video. There's more. This is the rest of the lab questions. They're really walking you through the same kind of proportion analysis, and I think you'll be all right. So I'll leave it at that, and I'll be posting another video soon. Okay, bye.